Hi students, we are going to discuss about moment of inertia. You already know moment of inertia I is equal to summation mi Ri square. In the expression for torque and angular moment of our rigid bodies, we have come to term that I, that is tau is equal to I alpha and L equal to I omega. Okay, this I is called the moment of inertia of bulk object. For point masses mi at a distance Ra from the fixed axis, the moment of inertia is mi Ra square. So I is equal to mi Ra square. For a bulk object, I is equal to summation mi Ra square. In translation motion, Mos is a measure of inertia. In the same way, for rotational motion, moment of inertia is a measure of rotational inertia. So its unit is kgm square. Dimensional formula for this moment of inertia is ml square. And mass is invariable quantity of matter except for motion comparable to that of light. But the moment of inertia of a body is not an invariable quantity. It depends not only on the mass of a body but also on the way the mass is distributed around the axis of rotation. We have considered an infinitesimally small mass dm as a point mass and take its position is r. So moment of inertia dA is equal to dm r square. So entire whole body, you take a entire whole bodies of moment of inertia. So I is equal to integral dA, that is equal to substitute the dA value, that is equal to integral dm r square. These integrations for determining the moment of inertia of some of the common bulk objects of interest like rod, ring, disc, sphere, etc. The next one is moment of inertia of a uniform rod. So let us consider a uniform rod of mass capital M and the length L. So the moment of inertia of this rod about an axis that passes through the center of mass and perpendicular to the rod. So origin O is to be fixed for the coordinate system so that it coincides with the center of mass, which is also the geometric center of the rod. The rod is now along the x-axis. Okay. So if first you take infinitesimally small, that is dm mass at a distance x from the origin. The moment of inertia of this small mass, that is di equal to dm x square. The mass is uniformly distributed. So the mass per unit length lambda is equal to capital M by L. Mass of infinitesimally small length dm equal to lambda dx. So you write the lambda value in dm. So m by L into dx. So substitute the dm value in moment of inertia. So I is equal to integrate the whole body, entire rod. So integrate the above equation, that equation di equation. So in I equal to integral di, that is equal to integral dm x square. So integral m by L into dx into x square. M by L is constant, take it outside of the integral. So m by L into integral x square dx. As the mass is distributed on either side of the origin, the limits for integrations are minus L by 2 to plus L by 2. So I equal to m by L integral minus L by 2 to L by 2 into x square dx. So integrate this x square, that is x cube by 3. So m by l x cube by 3, limitation minus l to l by 2. So the substitute the value for l by 2 in x cube. First you apply the upper limit l by 2. L by 2 whole cube. L by 2 whole cube, that is L cube divided by 8. 8 into 3 is 24 minus lower limit. So minus of minus L by 2, that is L cube by 8 divided by 3. So L cube by 24. So m by l into L cube divided by 24 plus L cube by 24. So 2L cube by 24. So 2 and 24 cancel. So that is 12. So m l cube divided by 12. So L cube cancel. So 1 by 12 ml square I is equal to, this is the rod, moment of inertia for rod. The next topic is rotational dynamics. The relation among torque, angular acceleration, angular momentum, angular velocity and moment of inertia you already know. We will learn the relations among the other dynamical quantities, that is work, kinetic energy in rotational motion of rigid bodies. Finally, a comparison between the translational and rotational quantities is made with the tabulations, that is effect of torque on rigid body. A rigid body which has non-zero external torque tau about the axis of rotation would have an angular acceleration alpha. So tau equal to I alpha. I is the moment of inertia of a rigid body. The torque is rotational motion is equal to the force in linear motion. And this tabulation is the moment of inertia for different rigid bodies. This one word. Object is thin uniform rod about axis passing through the center and perpendicular to the length. Then moment of inertia I equal to 1 by 12 ml square and radius of gyration k equal to 1 by root 12. Then thin rod, uniform rod, that is touching one end and perpendicular to the length, that is 1 by 3 ml square and radius of gyration 1 by root 3. And thin uniform rectangular sheet about an axis is passing through the center and perpendicular to the plane of the sheet. So I is equal to 1 by 2 m L square plus B square. Radius of gyration k is equal to root of L square plus B square by 12. And thin uniform ring about passing through the center and perpendicular to the plane is I is equal to ml square and radius of gyration is r. And the uniform ring touching the edge perpendicular to the plane, that is perpendicular tangent, that is I equal to 2 mr square and root 2 r radius of gyration. And the uniform ring that is passing through the center line the plane, that is I equal to half mr square, k is equal to 1 by root 2 r. And touching the angle edge parallel to the plane, that is parallel tangent about an axis, that is I equal to 3 by 2 mr square, k is equal to 3 by 2 root of 3 by 2 into r. And then uniform disc about an axis passing through the center and perpendicular to the plane, I is equal to half mr square. And the uniform disc, thin uniform disc touching the edge perpendicular to the plane, then I is equal to 3 by 2 mr square and k equal to root 3 by 2 into r. then passing through the center lying on the plane along diameter I is equal to 1 by 4 m r square, and of m r square is a gyration, radius of gyration touching the edge of parallel to the plane, so I is equal to 5 by 4 m r square. Okay, and thin uniform hollow sphere and uniform solid cylinder, and thin hollow sphere, uniform solid sphere, these are all in one word question.